Today, we're going to pull back the curtain on one of the most fundamental ideas in all of computer science, sorting algorithms. These are the unsung heroes of the digital world, the little engines that take total chaos and turn it into perfect, usable order. I mean, have you ever really stopped to think about it? You tap Sort by Date on your phone, and instantly, thousands of photos just snap into place. It feels like magic, doesn't it? Well, it's not magic. It's a seriously powerful sorting algorithm working at lightning speed. The question is, how? So, here's the game plan for today. First, we'll talk about why we even need to sort things in the first place. Then, we'll meet the simple sorters, the basic, entry-level guys. After that, we'll level up to the big leagues with divide and conquer. We'll pit them against each other in a showdown. And then we'll wrap up by looking at where you see this stuff in your day-to-day life. All right, first things first. Order from chaos. Imagine trying to find a specific book in a massive library where all the books are just thrown into random piles. It would be a nightmare, right? Well, data is exactly the same. Before you can find anything, you have to get it organized. And that, right there, is the whole point of sorting. So, let's get a quick definition on the table. Sorting is just arranging data in a particular order. Alphabetical, numerical, chronological, you name it. But here's the crucial part. How you do it matters a lot. Different algorithms have huge differences in their speed, how complex they are to write, the actual technique they use, and how much computer memory they eat up. Okay, let's dive into our first group, the simple sorters. I like to think of these as the fundamental exercises you do when you're first learning to code. They're super intuitive, really easy to wrap your head around, but as you're about to see, that simplicity comes at a price. First up, we've got bubble sort. We're calling this one the patient neighbor. Why? Because it's probably the most straightforward, simple sorting method you could possibly imagine. Its entire strategy is just comparing two items that are right next to each other over and over and over again. And here's exactly how it works. Bubble sort looks at two elements, side by side. If the one on the left is bigger, it swaps them. Simple. Then it just shuffles one spot to the right and does the same thing again. It keeps making these passes through the entire list, and with each pass, the biggest values kind of bubble up to the end. It just keeps going until it can make a full pass without having to swap anything. It's patient, but man, is it repetitive. All right, next on our list is insertion sort, or the careful builder. This one works almost exactly like how you'd sort a hand of cards you were just dealt. You pick up one card at a time, and you carefully slide it into its correct spot in the hand you're already holding. So, the process is pretty methodical. It grabs an element from the unsorted part of the list. Then it looks backwards through the already sorted part, shifting everything bigger one spot to the right to make a little gap. And then, pop! It inserts the new element right where it belongs. It just carefully builds up a sorted list from left to right. And the last of our simple trio is selection sort, which we're calling the perfectionist. This one's got a totally different mindset. It's obsessed with making the absolute best move every single time. So it scans the entire rest of the list just to find the single smallest item, and only then does it make a move. You can really see how deliberate it is here. On every pass, its one and only job is to find the absolute minimum value in whatever's left of the list. Once it finds it, it swaps that value with the very first unsorted element. One perfect swap. Then it moves the boundary over one spot and does the whole thing again. So, you've met the simple sorters. What's the final verdict? Well, here's the big problem. They all share the same pretty terrible performance, which we call O of n squared, or big O of n squared. Now, what does that actually mean? It means they don't scale well at all. If sorting 10 things takes a second, sorting 100 things doesn't take 10 seconds. It takes 100 seconds. The time just explodes as the list gets bigger. And that really brings us to the bottom line. These algorithms are fantastic for learning the concepts, but for any list that's even moderately large, they are just painfully slow. Trying to sort a million items this way, forget about it. And that's exactly why we need something smarter. And that leads us to our next level, the divide and conquer algorithms. Now we're talking about the pro-level stuff. Instead of just grinding through a list one item at a time, these use a much more elegant strategy. They break a huge problem down into much smaller, manageable pieces, solve those tiny pieces, and then cleverly put them all back together. First up is merge sort, the team manager. This algorithm is a master of delegation.
It takes a huge list and just splits it in half. Then it splits those halves in half. It keeps doing this again and again until it's just left with a bunch of tiny little lists with only one item in them. And, well, a list with one item is already sorted, right?
The real magic, though, happens on the way back up. After it's broken everything down, it starts merging. It takes two small, sorted lists and combines them into one slightly larger sorted list. And it just keeps doing that, merging and merging all the way back to the top, until, voila, the entire original list is back together and perfectly sorted. It's incredibly reliable. And now for the one that absolutely lives up to its name, quicksort, the fast pivoter. In the real world, this is often the fastest one of them all. Its whole game is to pick a random element, we call it a pivot, and then super quickly rearrange the whole list so that all the smaller stuff is on one side of the pivot and all the bigger stuff is on the other. So here's the strategy. You pick a pivot, then you just partition the list around it, everything smaller to the left, everything larger to the right. Now you've basically got two new, smaller sorting problems to solve. So what do? You just run the exact same process on those two smaller lists. Recursion at its finest. It's wicked fast on average, though it does have one tiny vulnerability. If you get unlucky and keep picking bad pivots, it can slow down. Okay, we've met all the contenders. It is time for the algorithm showdown. Let's put all 5 of these methods on the board, side by side, and see how they really stack up. And really, it all boils down to this fundamental trade-off. In one corner, you have the simple sorters. They're easy to understand, but they have that slow O(n)² performance that just dies when the lists get big. And in the other corner, you have the divide and conquer crew. They're more complex, for sure, but their O(n) log n speed is in a completely different league. We're talking the difference between waiting for minutes versus waiting for milliseconds. This table right here, this tells the whole story. You can see merge sort is an absolute rock star when it comes to consistency. O of n log n across the board. But check out that extra space column. It needs a bit more memory to work its magic. Now look at quicksort. On average, it's a monster, super fast, and it doesn't need that extra memory. But it's got that Achilles heel, a worst-case scenario that's just as slow as the simple guys. These are the exact kinds of trade-offs developers think about every single day. So let's wrap this up by bringing it all back to you. This hasn't just been some abstract computer science lesson. These algorithms are the invisible workhorses running behind the scenes of things you use every single day. Just think about the scale. A teacher sorting the grades for a class of 30 kids? A simple algorithm like insertion sort is totally fine, maybe even faster, because it's so simple. Your phone sorting your contacts? Same deal. But a massive social media company trying to organize data from 1 billion users? They are absolutely using a powerhouse like quicksort or merge sort. You have to use the right tool for the job. And that leaves us with one final thought to chew on. In this age of big data, it seems like a no-brainer to always go for the fastest, most complex algorithm, right? But is that always true? Could there be times, maybe with really small lists or data that's already almost sorted, where the simplicity and low overhead of a simple sorter actually makes it the better choice? The real answer, like with so much in technology, is it depends. Thanks for tuning in.